An hour and a half, should I? Think I'm gonna start today with the Italian thing. I did around 10 articles, I think, last time. And I used ChatGPT and I pretty much didn't change anything. I just copy everything from ChatGPT. So now I'm gonna review the articles. And I think that's a good strategy, is to do the articles off stream probably. Unless it depends on the flow of the situation where I stop off stream because I wanna be consistent with the stream. So whenever I stop, but I'll try to do articles off stream and then review them on stream because I think that's better. So I did a bunch of them. I think I'm gonna review them from the beginning, starting from the prims algorithm graph. And also the other thing that I fixed here in the way that these components are showing is I use something called flex row, I think, because they were not fitting the page really well. Yeah, so I did this flex flow row wrap, and it makes them look better when they are like this. Yeah. So I'm just gonna read through them and I'm going to check if the code is correct. If it is, I'm just gonna move on to the next one. And I think I'm gonna aim for, I think a very good aim is to try to do 10 articles a day, but I think that's gonna be extremely difficult. So, but I think I would like to have that as an aim, then probably be satisfied with anywhere between 5 and 7, I think. It's very good. But realistically, even one article a day, I think is very, very good. And the only reason I'm aiming a lot higher is because I can use ChatGPT to do most of the work, I think. And I saw a video from a guy today as well, where he talks about the whole thing about Google becoming worse, which I agree, and it's because of this thing that I'm doing here. But like I said before, I think this is inevitable because it's just a situation of it's just the byproduct of having the games, the way that the system is designed. So I don't think there is a way to go about it, but pretty much what he says is the stuff that was talking about as well, which is the moment you have all these AIs, then everyone starts doing the same content because the AI is gonna put very similar outputs for everyone because it's based on the large language model. So there might be deviations every time you do the prompt, but it's gonna be very similar for everyone and that's the problem because then it creates the cycle and then there's no creativity left because it becomes this vicious thing where everyone is trying to hack the SEO because people realize that attention is money. So everyone's trying to compete for attention and to get more traffic, to get more money. And it becomes this adversarial dynamics where people are gonna start doing what I'm doing now, and then there's going to be a bunch of people with articles that are pretty much the same. And then the problem with that is that if you want to find a solution for a problem, for example, that it didn't exist or that is relatively new or more complex, then it becomes really hard to find because people are hacking YouTube's recommendation system by reverse engineering SEO, and then it becomes this broken thing. And I think Google is not going to collapse because of this. I think that it's very likely that Google collapse because it has too much power and they have AIs as well and they own YouTube as well. But I think what is happening is because everything works in cycles, there's this fluctuation. So I think that Google is in a deflation state and it's probably going to last some time. And this happens with everything, I think. Like in the beginning, it starts rising, then it's good, then it reaches a peak, and then it starts declining. And I think that's just normal part of the evolution. But I don't think Google is gonna collapse because it's just too big. But then I was thinking that what's probably gonna happen because to solve this issue, and I think that's gonna happen. And then I was trying to think if I can come up with some product or something like that that is aligned with this, but I think it's too complicated for me for the stage that I'm at now. Maybe in the future I'll do something like this. Uh, I was trying to do this with the chain data thing. It was originally the idea I have. It's very similar, like it's on the same line, but for the blockchain. But what I think is gonna happen is that you're gonna have the same thing that happens with Shopify, but for search. So you're gonna have a very big platform that incentivizes people somehow to create web scrapers for it, and then the web scrapers are gonna become customizable and specialized on their field. And then obviously the platform that sustain the web scrapers makes the most money. So in this case would be Shopify for web scrapers, I think. And that's gonna become the new search engine system, I think. But the thing that I'm not really sure is how that's gonna, like the nuances of that. But I think that's the direction things are going. Because then if you think about it, it becomes a lot harder to gamify the SEO because there's so many different web scrapers. So you can't, and then what's gonna happen after is that people are gonna specialize in the niches of the SEOs, of the different SEOs. And I think that's going to create the same dynamic and eventually it's going to fluctuate until it gets to a natural equilibrium, I think. But the thing that might be contradictory to this is that if you think about search, is a lot more complex than this because what you have to do to solve search is a very complex and pretty much impossible, I think, to figure out because what you're trying to do is to find the optimal solution for solving someone's problem in relationship to whatever is happening right now, which requires an infinite amount of complexity because there's always going to be more potentials and things that can happen. And that's the thing that I think, that's the reason why I think that it's unlikely that Google will uh, fail, let's say, because they probably have very powerful machine learning models with a bunch of data that they can abstract the archetypes of the collective consciousness, and then they can use all these powerful algorithms to optimize the search patterns. So the only problem is that they are getting into this vicious cycle, and it's probably because of complacency and the natural following the path of least resistance because everyone wants to make money and the corporation itself is like a bunch of people and then everyone has their own goals inside of the corporation. It becomes a really complex thing. But the issue with creating the other site that is the platform with the web scrapers is this problem of understanding how to use the data to optimize for solving someone's problem and not rely on these vicious cycles of behavior that either the attention economy of people hacking SEO to get to the top or to use the data to make money. Like and that's the reason why I was thinking about chain data because it's the same thing. I think Google doesn't want to go to the blockchain because it goes against the model they have. Because in the blockchain, depends on what kind of blockchain, but I think eventually because blockchains will move towards zero knowledge proofs and there's probably going to be, well, there is privacy if you incorporate zero knowledge proofs, but then there's more centralization as well. But I think if things go towards that direction, I think there will be a version of Google for the blockchain, and there might be some intersection there where you can make web scrapers for blockchain. And then I was thinking about the ideas, the whole concept of a searcher in the blockchain and how that relates to Google. Because the difference is that in the blockchain, the searcher is someone that is looking for MEV, and then the block builders are the ones that make the most money out of the searchers by knowing their transactions, and then you have to pay the gas to outcompete other searchers, and it gets to the point where the miner makes the most money. But still, searchers are incentivized to find the alpha because that obviously makes money. So, but the difference is obviously that most of MEV that comes from the blockchain is either from hacks, like they can be considered unethical, like sandwich attacks and front running. And the other huge part of MEV is the decentralized arbitrage. And then I was thinking, that led me to thinking about the arbitrage of content as well. Because most of their startups that are being made nowadays is pretty much ChatGPT built, is something built on top of ChatGPT. So they're pretty much arbitraging content. And I think it makes a lot of sense if you think about it because arbitrage is the computation of the system. Like is the osmosis of the system that updates over time. So in the same way that it works with money, it works with content as well. And it pretty much can work with everything, I think, because it's like waves on the electromagnetic field of human consciousness, if you think about it. And then the reason why they have differences is because of the friction on space-time and the difference in geometry in space-time, because the difference in geometry incentivizes differences in the electromagnetic field, which change the computation of the collective consciousness on the region of space-time. And then those differences make or generate waves, and those waves have this friction, and while there's these differences, there is opportunity for arbitrage in everything, and then it reaches a balance through osmosis. So there might be something that is similar to what a searcher would be in the blockchain for something like Google, that is a search engine that involves arbitraging content through web scrapers to create a platform of web searchers that, and then Google in this case, or the search engine that would work as the platform would be the block builder. But then the question is, how do you make the money from the searchers, which would be the, well, actually, that's a very great idea. I think that's going to happen, actually. So what's going to happen is that people that have these AIs like ChatGPT and all this other stuff are going to arbitrage the content through searchers. So searchers are going to be incentivized to do this arbitrage based on the gap of knowledge and the update of the system. So and I think that's going to happen as well because of the battle for disinformation, so that each searcher is going to serve as a gateway of truth, let's say, a portal of truth, and then there's going to be reputation on the searchers, and that's going to create a network of search, I think. But the only issue with this is that maybe I would try to do this, but it seems too complex and too big to be something that you start from. Ideally, I want to start with something that is more niche and specific, because I think that's more grounded. So I think, but that's the direction I think I'm going to go with eventually. But first, I want to think about something that might give me money now through the blog. But I think what I'm going to do now is do the merch here. I took a bunch of pictures from Midjourney, and I'm going. The site that I decided to go with for now is this one, because a couple of people said it's the best, but I'm not really sure, and I don't want to spend a lot of time thinking about this. But I'm going to create a section on the blog for merch, and I'm going to use the Midjourney's pictures for that. But after that, I'm thinking about different ways that I can incorporate Web3 into the blog, and I think that, and I want preferably to make something that is aligned with this vision of the future of this, the connection between arbitrage, the flow of the electromagnetic field, and the relationship with space-time, and the intersection of artificial intelligence and the blockchain. I think that's gonna be what's gonna happen. So yeah, but the only issue for that is that I need to, maybe I'll start my own node at some point after I finish all these articles here. I think that might be a good idea, because now I have because that's the only downside of doing the things on the blockchain. I either have to build my own nodes, and I don't have memory here to build a full archive node, but I can do the other version of the node, and I would be able to get a lot of information. So I might do that. But or I can use an archive node. But that's what I'm thinking about doing, like creating algorithms for searching the blockchain, searching for information of wallets in the blockchain, and then connecting them to the blog to allow people to visualize the data of the blockchain. And then later on working on search engines for the blockchain that incorporate these concepts of the relationship between searchers and block builders. But ideally, I would want to be on the block builder side, obviously. But I don't know how to do that. Like, what would be the analogous to that in the arbitrage content thing? Now let's do this shit here. Oh, did I run it on the wrong file? Maybe. So I want to think more about this of what will be the block builder of arbitraging content. If searchers were arbitraging content instead of arbitraging MVV, how would the block builder look like? I think I ran it on the wrong file. I had to go to speak. Fuck, now I don't know if I should delete this stuff here. Yeah, whatever, I'm just gonna leave it there.
Fa,
Don't use this anyway. Fa,
Does.
fisso.
fisso,
Set. Unchanging.
3.
3,
3.
Desiderare.
desiderare,
Desire.
Aria.
aria,
Air.
Bene.
bene,
Well.
Anche.
anche,
Also.
Giocare.
giocare,
Play.
Piccolo.
piccolo,
Small.
Fine.
fine,
End.
Mettere.
mettere,
Put.
Casa.
casa,
Home.
Leggere.
leggere,
Read.
Mano.
mano,
Hand.
Portare.
portare,
Carry.
Grande.
grande,
Large.
Compitare.
compitare,
Spell. Words.
Aggiungere.
aggiungere,
Add.
Anche.
anche,
Even. Also.
Terra.
terra,
Land.
Qui.
qui,
Here.
Devo.
devo,
I must.
Grande.
grande,
Big.
Alto.
alto,
High. Tall.
Tale.
tale,
Such.
Seguire.
seguire,
Follow.
Atto.
atto,
Enact.
Perché.
perché,
Why.
Chiedere.
chiedere,
Ask.
Maschi.
maschi,
Men.
Cambiamento.
cambiamento,
A change.
È andato.
è andato,
He. She went.
Luce.
luce,
Light.
Tipo.
tipo,
Kind. Of thing.
Spento.
spento,
Turned off.
Bisogno.
bisogno,
Need.
Casa.
casa,
House.
Immagine.
immagine,
Image.
Provare.
provare,
Try.
Noi.
noi,
Us.
Di nuovo.
di nuovo,
Again.
Animale.
animale,
Animal.
Punto.
punto,
Point.
Madre.
madre,
Mother.
Mondo.
mondo,
World.
Vicino.
vicino,
Near.
Costruire.
costruire,
Build.
Se stesso.
se stesso,
Himself.
Terra.
terra,
Earth.
Padre.
padre.
Father.
Yeah, I think the only issue with this thing of the creating the whole arbitrage content and a platform for web scrapers is that for in this analogy, in order for you to be able to be the block builder, you would have to have a bunch of data centers with machine learning models, I think, because the only way you would be able to rank, like in the analogy, the block building would be ranking the content. So instead of ranking the transactions based on which one is going to increase the gas fee, you would have to be ranking the content in relationship to what's more likely to solve the problem or to find what the person wants. And that's the issue with this, is that the only way to do that is having a bunch of data and then creating a very powerful model that is capable of approximating like the intent of the person of the search with the results that they desire. And that's extremely difficult to do. That's the reason why I think that Google is not going to be over, let's say. I think is likely on a deflation state, but it's gonna go back again at some point. But maybe I'm wrong. Yeah, but the reason why I said all this stuff is that obviously I'm thinking about this because I'm doing the blog, and the whole point of this is to rank on SEO. So I want to try to see if I can predict what's gonna be the next shift. And obviously video is obviously everyone says that now is more video, but I think like written text is not going to go anywhere for a very long time. Same reason why we have books today is just a different form of observing content. It's just going to change over time. And obviously I don't want to make a lot of videos because I think making videos for TikTok and things like that, it just takes a lot of work and is not very efficient, I think. Because then instead of doing that, I can just find a job and save money from the job and then build an app or something like that. I think that's more efficient. The current way that I'm looking at it is I'm looking for jobs now and I'm building this thing. And then if this starts giving me enough income, then I'm gonna use the income from this to invest in poker, which I already know how to play, and I'm also making money from poker as well. So I'm just gonna invest this into poker so I can climb up the stakes to make more money, and also use this to create the Web3 integrations and things like that. So I don't view this as an end goal, more of something that can increase the probabilities that it will open doors for me. And at the same time, as I build this, I'm going to gain a lot of knowledge as well by making all the articles. So that's the main thing I see from this thing here. But I also want to think about the direction things are going, and because obviously when problems are opportunities, like it's a symmetry. So whenever there's something that is a problem, it means that you're gonna have opportunities. And I think that given the state of the way things are, I want to try to avoid having to make videos, because I think that takes a lot more work than building the articles. That's the reason why I think I'm gonna stop making videos for now for the second channel, and I'm gonna write more articles, because the other problem that I really don't like about making videos, and this might be true for articles as well, but I'm not really sure because I don't view them as in the same way, is that when you make videos for YouTube, you have to stay on a certain niche, and I really don't like that because it goes against the way that I think about things. I want to integrate a bunch of areas as possible, because I think ultimately that's the thing that will allow me to solve very complex problems, because the market economy incentivizes specialization, but there's a capture specialization where it's better in the beginning, but because human beings are not scalable, then it becomes exponentially worse for more and more complex problems, because it becomes exponentially harder to coordinate large amounts of people. So let's say if everyone specializes, then you have to hire a bunch of different people and coordinate those people in order to achieve a higher goal, and that's what a company is supposed to be. But because of the way that the systems work, is not very efficient. So in order to try to be aligned with the long-term vision that I have, I can't really, I don't think it's a good idea to specialize a lot on only one thing. I think it's better to try to keep a ratio of specialization. I need to have some degree of specialization, but I need also to study all these other different areas as well. And making video content is not going to allow me to do that. But with the blog, I think it's different, because the way that I see the blog is more like different channels of communication that you can open up with different people. Because when you go to a blog, you don't necessarily care if they have other articles or other things like that that are not related to what you want. As long as they have a lot of information related to what you want, you can stay on that portion of the blog. So creating a blog is more like creating a platform, and the way that the SEO works is different than the way that the SEO works for ranking videos on YouTube. I think the machine learning model is different but this is the thing that I'm not really sure, and I might be wrong about this, because it might be the machine learning model might associate the whole structure of the graph with all the other data from the internet in order to derive the ranking of the graph, the ranking of the websites. But I think my intuition says is very different, the way that blogs are ranked and the way that videos are ranked. And blogs allow you to have more breadth, and videos force you to be more specialized. But I might change what I'm doing at any moment.
Prim's algorithm. Introduction to Prim's algorithm. Prim's algorithm is a widely used method for finding the minimum spanning tree, MST, of a weighted, connected graph. Developed by Robert Prim in the late 1950s, the algorithm has become an essential tool in computer science and engineering, with applications in fields such as networking, transportation, and telecommunications. In this article, we will discuss the basic principles of Prim's algorithm, its implementation and complexity, and some of its key applications. By the end of this article, readers will have a strong understanding of Prim's algorithm and its potential to solve real-world problems. Understanding the minimum spanning tree. Before diving into Prim's algorithm, it is important to understand what a minimum spanning tree is and why it is useful. A spanning tree of a graph is a tree that includes all the vertices of the graph, with a minimum number of edges. The weight of a spanning tree is the sum of the weights of its edges. A minimum spanning tree, MST, is a spanning tree with the minimum possible weight. Finding the MST of a graph can be useful in a variety of situations. For example, in telecommunications, the MST can be used to find the most cost-effective way to connect a set of cities with telephone lines. In transportation, the MST can be used to find the most efficient route for a trucking company to take between a set of cities. In networking, the MST can be used to find the most reliable way to connect a set of computers in a network. Understanding Prim's algorithm. Prim's algorithm is a greedy algorithm that is used to find the MST of a weighted, connected graph. The algorithm starts with an arbitrary vertex, and at each step, it adds the next closest vertex to the current tree. The algorithm continues until all vertices have been included in the tree. The basic steps of Prim's algorithm are as follows. Start with an arbitrary vertex as the first vertex of the tree. Add the vertex with the smallest weight that is connected to the current tree to the tree. Repeat step 2 until all vertices have been included in the tree. One of the key features of Prim's algorithm is that it is a greedy algorithm. This means that it makes locally optimal choices at each step, without considering the global consequences. While this can sometimes lead to suboptimal solutions, it also makes the algorithm relatively simple to implement and understand. Implementing Prim's algorithm. There are several ways to implement Prim's algorithm, including the lazy and eager approaches. The lazy approach is more efficient for dense graphs, while the eager approach is more efficient for sparse graphs. The lazy approach involves maintaining a priority queue of the vertices that are not yet in the tree. At each step, the vertex with the smallest weight is removed from the queue and added to the tree. The eager approach involves maintaining a priority queue of the edges that connect the tree to the vertices that are not yet in the tree. At each step, the edge with the smallest weight is removed from the queue, and the vertex at the other end of the edge is added to the tree. Time and space complexity. The time complexity of Prim's algorithm is O, E log V, where E is the number of edges and V is the number of vertices in the graph. This makes the algorithm relatively efficient for both dense and sparse graphs. The space complexity of Prim's algorithm is O, V, as the algorithm only needs to store the vertices and edges in the current tree. This means that the algorithm does not require a significant amount of memory, even for large graphs. Applications of Prim's algorithm. Prim's algorithm has a wide range of applications in computer science and engineering. Some of the most notable applications include network design. Prim's algorithm can be used to find the most cost-effective way to connect a set of computers in a network. This is known as the Steiner tree problem, and it is often used in telecommunications and networking. Transportation. Prim's algorithm can be used to find the most efficient route for a trucking company to take between a set of cities. This is known as the traveling salesman problem, and it is often used in logistics and transportation planning. Clustering. Prim's algorithm can be used to find clusters of similar data points in a dataset. This is known as the single linkage clustering, and it is often used in data mining and machine learning. Image segmentation. Prim's algorithm can be used to segment an image into different regions. This is known as the minimum cut problem, and it is often used in image processing and computer vision. Conclusion. Prim's algorithm is a powerful and widely used.
Yeah, so here I think I'm gonna change this. I'm gonna put the implementation before the conclusion. The rest seems fine, I think. I just have to check to see, but I think Prim's I've looked into it enough. The other ones I didn't look too much into the code to see if it's correct, but these ones I think but obviously I'm gonna spend time thinking about it. It's always about trying to reach the balance, I think, of doing things really fast, but at the same time being careful to make sure that is very likely correct. Obviously, you can never know 100% because it's a gradient. You never know the truth 100% because everything you know is relative to your experiences, and everything could be wrong at all times. So that at the extreme of this, you wouldn't be able to do anything because you can never know for sure if you know anything, because everything is a self-fulfilling prophecy. Because the cause and effects relationships that you assume to be true are relativistic to your current identity that creates the nature of the present moment for you. So at the other end of the gradient, you become extremely close-minded because you think everything you know is 100% true, an absolute fact, which is also not accurate, because if that was the case, then there wouldn't be any potential for anything new. So the optimal approach is always trying to find the natural equilibrium of those two ends of the spectrum that is going to depend on whatever circumstance you're experiencing. In my view, obviously I can be wrong.
Prim's algorithm. Introduction to Prim's algorithm. Prim's algorithm has a wide range of applications in computer science and engineering. Image segmentation, Prim's algorithm, Python naive/simple implementation. Import heap.
This one is terrible for the audio, the voice is terrible for code. Okay, so creates the minimum span tree with a set, then the priority queue, heapifies the priority queue, which means it's gonna create the structure where the first element or the element of the top is the smallest. Then it pops the thing and makes the weight, gets the first and the vertices, the vertex is the start node. So it checks to see if they are, then continues, otherwise it has them. Then it goes over the neighbors of the current node, current vertex, and then pushes them to the heap queue. And because it's pushing them, then the last one that in the other loop is gonna remove the one that is the smallest out of the neighbors. So I think I get it, and I think it's correct. So it pretty much goes on a loop. It checks for the neighbors of the vertex, the current vertex, and then because it's putting on the heap, it's gonna on the priority queue that is heapified, is gonna take the minimum when it pops, the smallest amount when it pops on the next iteration of the loop. And when it does that, it sends the nodes to the MST, because the minimum spanning tree is the connection of all the nodes on the graph that doesn't involve a cycle, if I remember correctly. So because you want the smallest, you want to use the heap, and yeah, makes sense. I think I understand how this. Obviously, to implement these algorithms, I don't think I'm gonna become very good, because even if I understand them, it's one thing to read them, and it's another thing to come up with the solution yourself. So I think that by doing this, I'm not gonna become very good at coming up with the solution myself, but I'm definitely gonna become good or better at understanding. And this goes into the stuff that I was saying before, where it's all about the balance, because even though I'm not going to be able to, I'm not going to be extremely good at coming up with the solution, I'm going to have a vast understanding of all of the algorithms, I think, which is going to make me better at thinking about the problems, I think. So the issue is that if I spend too much on this, then it goes back to what I was saying, where I'm gonna be too slow, I think. And timing is everything. So But I obviously don't wanna go too fast either. I wanna make sure that I understand what I'm doing. So here, I guess you don't need to create a heap. The moment you use this, it depends on the class that comes from the import here. And it's pushing to the heap the priority queue, which is the tuple that has the weight and the nodes, the two nodes, the current one and the neighbors, I think. Yeah, because it goes on a loop through the neighbors, and if they are not in the MST, it pushes them. It pushes the neighbor, pushes the priority queue, then the neighbor, then the vertex and neighbor. It pushes the weight of the neighbor. The weight of the neighbor, the vertex and the neighbor. It makes a lot of sense. And then the next one is gonna get the one that is the smallest. So I think it's correct.
This function takes in a graph represented as an adjacency list in a starting vertex, and returns a set containing the vertices of the MST. The heap library is used to implement a priority queue, where the priority is the weight of the edge. The algorithm starts by initializing an empty MST and adding the starting vertex to it, and adding all edges adjacent to the starting vertex to the priority queue. The while loop continues until the priority queue is empty. In each iteration, the edge with the smallest weight is extracted from the priority queue, and the vertices of the edge are added to the MST if they are not already in the MST. Then, all edges adjacent to the new vertex are added to the priority queue. Conclusion. Prim's algorithm is a powerful and widely used method for finding the minimum spanning tree of a weighted, connected graph. With its simple implementation and efficient time and space complexity, the algorithm has become an essential tool in computer science and engineering. Whether you are working in telecommunications, transportation, or data mining, understanding Prim's algorithm and its potential applications is essential for some.
One thing that I realized already is that it's very common to transform a graph into a tree. And the reason why is because tree is probably more optimized to find the smallest and highest value through this heap thing. So there's this relationship between graphs and trees. Obviously, the whole point of the algorithm is to get the minimum spanning tree, but I'm saying in a more general sense, I think that there are probably a subset of problems that involves this relationship between graphs and trees. And I think one of the reasons I think that might be the case is because of the flow of the information. I think when I think about genetic mutation, I think about the same thing, which is a normal probabilistic distribution, which is relative to the radiation or to the flow of the electromagnetic field in relationship to the DNA. And I think that's the flow of information. You see the same pattern in hardwares as well, where the more, and I think that's the fundamental relationship of space-time and the electromagnetic field, because that's what happens with hardware. The more space you have, the slower it becomes because it has more gravitational force, so it's denser. And the faster it is, the less memory it is. And the entropy of an identity is this funnel of information. That is a multifractal pattern that creates the experience of space-time in relationship to an identity. So I think it's the same pattern here, and I think that's probably the reason why there is this fundamental relationship, but I might be wrong, obviously. But if you think about a graph, the graph would be space-time, and then the tree would be the electromagnetic field, like being shaped through the space-time in relationship to whatever is the geometry of the problem you're trying to face or to solve. And that's why it's always relativistic. And usually it's probably because of energy flow through the path of least resistance that you usually want to derive either the max or the minimum value from the graph. So if I ever do the archetype thing, that's a good thing to keep in mind. I think I'm gonna talk about that. I think this is a good way to think about it. I do a bunch of different articles with ChatGPT. Then I extract a bunch of information, do synthesis on my mind over the common topics, common things, patterns I see, and then if I get penalized through Google and I see that I'm not growing by just doing the ChatGPT, then I'll create this funnel of the synthesis. And in that way, I think I'm gonna be able to maintain or to grow in relevancy, because it's one of those things that I think that in the future, what's gonna be very valuable is gonna be integrity, and because you always need this, and it's gonna become more and more relevant, because the more misinformation you have, the more powerful it becomes, the more difficult it becomes to have sense making, and I think this is already happening. So people are gonna need to rely on sources that are trustworthy, and trustworthiness is directly correlated with integrity, I think. And that's the mechanism of reputation. That's why it's very important to remain, to keep your integrity, I think. But it's always a very hard balance, though. It's not very obvious, because morality and ethics is always changing, so everything is always relativistic. Like if you look from a Nietzsche standpoint, I think it was Nietzsche that said something like that. That is everything is dependent on power. I think I disagree with this slightly, because I think it's a part of the symmetry where if you think everything is about power, you lose the other side of the symmetry. The notion that everything is about power is more the scientific, rational parts of the brain, which is related to the masculine and related to patterns. But then you lose the potential and the data and the chaos that create the patterns in the first place, and they are entangled. So, and that's the path of spirituality, I think, that it closes the feedback loop or the cycle. And the cycle is actually a spiral, because the beginner is the beginner is identical to the master, but with 360 degrees differently of the difference. So they look the same, almost the same, but the reason why they do things they do is completely different, because the why of the master has a much better, much deeper connection of reasons, and the beginner just does it out of ignorance. So they take very similar actions, but the master is grounded into a lot more complexity. So it becomes simple again, but in reality is far more complex, because it's grounded in all these subconscious things. And I think it's the same pattern where at first you believe everything is power because of the dynamics of, and I think that's what's happening with society as well, with evolution. And the extreme of that is Hitler, where if everything is about power, then the only thing that matters is the superior race. And then we know that this is self-destructive, because the fundamental issue is that you can't win the game by only focusing on winning the game, because that means that you are gonna kill the parts of yourself that create the game in the first place, which are the different parts of yourself that you are competing with to beat the game. So it's kind of a paradoxical thing. That's why I think that's probably the closest to Nash, I think, is more of a holistic approach that yes, power is important, but it's not everything, because if you think like that, you're gonna get into a vicious cycle of self-destruction, because you need to realize that you are everything. So if you try to win, then by power, that means you are maintaining only the parts of yourself that are not integrated with everything else that makes up what you are. So in order to truly win, you have to let go of some of the power, I think, because you need to give space for other things that are not directly attached to the physical properties of your body to exist, in order for your body to exist. And in that sense, the power would be not winning. So it seems like you're winning, but in reality it's not. And I think the reason why a lot of people think like that is because of the limbic system. Like the limbic system doesn't have a understanding of the context. So it's the more animal part of yourself that is not conscious. So you can't see that, and that's the reason why people get addicted to things. Like you can see that the dopamine spikes you get are going to become pain eventually. But then that's when you get to the paradox as well, because if you go too much in the conscious side, then you become depressed because of loss of meaning, and yeah, the Nash is probably both perspectives at the same time, or close to the Nash, I would say, because I don't think that the Nash is probably a paradox. So you can't achieve the paradox through knowledge. I think you have to go somewhere a different way, but I'm not really sure how. Has to come from a different way. Okay, this one is the next one.
Whether you are working in telecommunications, transportation, or data mining, understanding Prim's algorithm and its potential applications is essential for solving real-world problems. Kruskal's algorithm. A comprehensive guide to understanding and implementing the algorithm. Kruskal's algorithm is a popular algorithm for finding the minimum spanning tree, MST, of a graph. It is a greedy algorithm that is used to find the optimal solution for a wide range of problems, including network design, image segmentation, and cluster analysis. In this article, we will delve deep into the workings of Kruskal's algorithm, its implementation, and its various applications. Understanding Kruskal's algorithm. The minimum spanning tree of a graph is a tree that spans all the vertices of the graph and has the minimum possible total edge weight. Kruskal's algorithm is used to find the minimum spanning tree of a graph by iteratively selecting the edges with the lowest weight and adding them to the tree until all the vertices are spanned. The algorithm starts by sorting the edges of the graph in increasing order of their weight. Then, it iterates through the edges, adding each edge to the tree if it does not form a cycle. If the edge forms a cycle, the edge is discarded, and the next edge is considered. This process continues until all the vertices are spanned, and the tree is complete. Pseudocode for Kruskal's algorithm. Kruskal, G. Sort the edges of G in increasing order of their weight T equals for each edge, U, V, in G if T plus, U, V, does not form a cycle add, U, V, to T return T. Implementing Kruskal's algorithm. Kruskal's algorithm can be implemented using various data structures, including arrays, lists, and sets. The most common data structure used for implementing Kruskal's algorithm is the disjoint set data structure, also known as a union find data structure. A disjoint
This one I remember I spent a lot of time in the previous stream trying to understand what it is. But I think I'm gonna spend more time now as well, because I don't remember really well. But I know that it's something that joins through sets, through some form of group or something like that. I don't remember really well.
A disjoint set data structure is used to keep track of the connected components of the graph. Each vertex is initially in its own set, and as the algorithm proceeds, the sets are merged as the edges are added to the tree. The disjoint set data structure is used to efficiently check if an edge forms a cycle by checking if the vertices of the edge belong to the same set. Python implementation.
At this part, I'm gonna have to think about. Okay, so it starts off with a bunch of different sets, I think. Each one of them with its own vertex or node. And then as the nodes are added to the tree, the sets are joined, I think. As the edges are added to the tree. And this checks to see if there's a cycle. Yeah, I don't understand this one. I'm gonna use ChatGPT and YouTube and Google to clarify that one. Actually, I need to ask for disjoint data sets or disjoint sets and union.
Okay, let's talk about a really neat application of the union find, which is Kruskil's minimum spanning tree algorithm. So you might be asking yourself, what is a minimum spanning tree? So if we're given some graph with some vertices and some edges, the minimum spanning tree is a subset of the edges which connects to all the vertices and does so at a minimal cost. So if this is our graph with some edges and some vertices, then a possible minimum spanning tree is the following. It has edge weight 14, total edge weight 14. And note that the minimum spanning tree is not necessarily unique, so if there is another minimum spanning tree, it will also have a total weight of 14. So how does it work? So we can break it up into 3 steps essentially. So the first step is easy. Just take our edges and sort them by ascending edge weight. Next thing we want to do is we want to walk through the sorted edges and compare the two nodes that the edge belongs to. And if the nodes already belong to the same group, then we want to ignore it because it'll create a cycle in our minimum spanning tree, which we don't want. Otherwise, we want to unify the two groups those nodes belong to and keep going. And we can do this process either we run out of edges or all the vertices we unify into one big group. And this is what I mean by big group, which is when our unified instructions come play. So if this is our graph, then to run Kruskil's algorithm, first let's see all the edges and sort them. So on the left side, you see I have all the edges and their edge weights sorted in descending order. So next we're starting the edges one at a time, starting with the top. So ij. So I started with the edge ij orange, and you can see that connects nodes ij. ij currently don't belong to any group, so I'm going to unify them together into group orange. Next is edge AD. So AD don't belong to a group, so I'm going to unify them together into group purple. Next is C to I. So I belongs to group orange, but C doesn't have a group yet, so C can go into group orange. Right? E to F doesn't belong to a group, so F can go to group purple. Next H and G. Neither H nor D belong to a group, so I'm going to say you guys belong to the red group. Next we have D to B. They also belong to a group, so give them their own group. Let's say group green. Right now, I believe this is when things start getting interesting. Now we're trying to connect C to J, but notice that C and J already both belong to group orange, so we don't want to include that edge because it's going to create a cycle, so we ignore it. And to check that they belong to the same group, we would use the find operation in our unified to check what group they belong to. So this is when the unified really comes into play. Next is edge DT. So note that.
Oh, and I think I understand now. Because it was difficult for me to understand because I was thinking about nodes, not edges. But it makes sense that because in the beginning you start adding the edge to the set, and the set's gonna be the connection between the nodes. So if you find other nodes, then it has the same connection that is already on the set. It means that it's a cycle. I think I understand now.
E belongs to purple and D belongs to group green. So now we want to merge them together because they all belong to the same group. So either the purple group is going to be green group or green group is going to be purple group. It doesn't matter. So I would merge them, and this one the union operation in our union find can allow us to merge groups of colors
Let
together.
me go back to
So
this.
I would merge them, and this one edge DT. So note that when we create a cycle, so we ignore it. And to check that they belong to the same group, we would use the find operation in our union find to check what group they belong to. So this one the union find really comes into play. Next is edge DT. So note that E belongs to group purple and D belongs to group green. So now we want to merge them together because they all belong to the same group. So either the purple group is going to become the green group or the green group is going to become the purple group. It doesn't really matter. So I would merge them, and this one the union operation in our union find comes useful. It allows us to merge groups of colors together very efficiently. And that's the important note. Next D. So note that E belongs to group purple and D belongs to group green. So now we want to merge them together because they all belong to the same group. So either the purple group is going to become the green group or the green group is going to become the purple group they belong to. So this one the union find really comes into play. Next is edge DT. So note that E belongs to purple and D belongs to group green. So now we want to merge them together because they all belong to the same group. So either the purple group is going to become the green group or the green group is going to become the purple group. It doesn't really matter. So I would merge them, and this one the union operation in our union find comes useful. It allows us to merge groups of colors together very efficiently. And that's the important note. Next edge would be D to H. H belongs to group red and D to purple. So merge the groups together. Let's say they both become group purple. Next up, we want to add edge A to D, but A to D already belong to the same group, so that would create a cycle. So we don't want to include that edge. So skip it. Next, we want to include edge B to C. B to C belong to different groups, so merge the two groups into one larger group. So we have found the minimum spanning tree using Kruskil's minimum spanning tree algorithm. Pretty neat, right? So the underlying data structure which allows us to do this is the union find. It allows us to merge groups of colors together efficiently, but also to find out which groups nodes belong to, so that we don't create a cycle. So that's Kruskil's algorithm. It's super simple, given that you know how the union find works. So I'm going to go into some detail in the next video explaining how the find and the union operations work internally and how we can actually implement it in some useful way. All right, I'll see you guys then. Bye.
I think I sort of understand, but I wanna make sure. I understand the concept, but the code is still hard to understand. It sorts the edges first, then gets the parents. No more vertices. I think this one is easier to understand. I'm gonna use this one rather than the other one that I have there. But this one doesn't have. Oh no, we have this here. So it has the vertices. Yeah, so U and V are the edges. So it's the connection between U and V. And the W is the weight. Defines union functions. Yeah. Union parents unit. I don't understand really well how the find works. So where's the parent here? So parents are all the vertices. Number of vertices in the graph. So I don't understand really well. Like it goes recursively until the item on the parent is the same as the vertex in the find function. But what does that do? It's passing the parent, and then the I becomes the parent I. Just searching on the parents to see where's the node. Yeah, I think I need to understand the find function.
So let's begin by talking about what union find does. Imagine that you have some objects and you want to group them together according to some criteria. So one such grouping might be this. Now, once you have completed grouping, you would want to know certain properties of groups, such as how many groups there are, and if two objects belong to the same group. The union find data structure, as the name suggests, supports two operations. The first one is called union, which takes as input two elements x and y from a set of objects, and it joins or unions the groups containing x and y. For example, we can start with 0 and 2 belong to the same group, and 1 and 3 belong to the same group. And when we call this function union 0, 1, it joins or unions the groups containing 0 and 1. So the final result will be all 4 objects belonging to the same group. The next operation is called find, and it takes a single object x as the input and returns the group that x belongs to. So now let's see how we can implement union find. We will first walk through the ideas and discuss the code at the end. Union find is useful in graph type problems. So our first step will be to cast the grouping in the form of a graph. And the way we do that is to connect all the objects that belong to the same group with an edge, like so. Now, remember, we need to find a way to determine which group each element is in. To do so, we designate a representative element for each group. This element will represent the entire group it belongs to, in the sense that the find function will always return the representative. For example, when we call find of 4, the representative of the group that 4 belongs to is 0, so therefore we return 0. And of course, the representative will return itself. As another example, when we call find of 2, we return the representative of the group 2 belongs to, which is 5. Notice that two elements belong to the same group if and only if they have the same representative. So the representative provides a way of checking if two elements belong to the same group. So now we need to implement the other function, which allows the union of two groups. And
Yeah, so I think I understand. So in this case, the find is I think this is the old one. And the find is used, so this creates the, yeah, but why because this is supposed to be the sets, the different sets of the edges. I don't understand why it's done here. Because it's making a list of all the nodes, of all the numbers of vertices. So a list that has the length of all the numbers, I think, of all the vertices. So if they are different, it means that they are on different sets. And then you append to the MST. And then you join the sets based on the parent. I think I get the algorithm. I'm just trying to make sure that I understand this connection between this find function here. I think that's the one that I'm struggling to understand. I always struggle to understand recursion. But what I think is going through a loop is searching all the elements of this parent to see if the whatever node is passed, it is included on here, but it searches until it finds the node in the parent here, and then returns the node. I think what this does is check for the cycle. That's the function that checks for the cycle. Because if they are the same, then it means that there is a cycle. So they have to be different for the thing to be appended. I think that's what's happening. But I'm not really 100% sure. So I'm gonna watch a couple more videos and maybe read ChatGPT there. But I think I'm pretty confident that this is a correct solution for this. Because it makes sense. The confusion I had in the beginning is that I didn't understand that it was doing by edges, and I was thinking about nodes instead of thinking about the edge. But now I get it, I think. And the only thing that I'm still not sure is why it's creating the list with all the... because I don't understand what this is. So it says your number of vertices in the graph. But what does it mean? Like when you pass inside of here, is what is the graph? It's a dictionary. And so it's gonna create the list with the, because the range, let's say there's 10 nodes. The range is gonna be range 10, and then the list is gonna be a list of 10 items from 0 to 10. But I don't understand how the node is mapped through that. The edge is mapped through that.
And to do that, let me rearrange this graph in a suggestive way. I now put the representatives at the top and the rest of the elements of the group towards the bottom. Now, each group is represented as a tree, with the root being the representative. With this, we can introduce the notion of parents and children. For any given element, how do we find the representative? Well, we must travel upwards the tree towards the root. In other words, we need to keep traveling towards the parent until we reach the top. As an example, suppose we want find of 4. The parent of 4 is 3, so we travel upwards to 3, and the parent of 3 is 0, so we travel up to 0. And we will know when to stop if we just use the simple convention that the parent of a root is itself. So if we can keep track of the parent of every object, then we can very easily travel upwards the tree towards the root. So what about the union operation? Well, in this new interpretation, the representatives are the roots of the trees. So if we want to union two trees, we can just set the root of one tree to be the child of another. For example, suppose we want to union 1 and 2. 5 is the root of 2, which we can get by calling find of 2. And similarly, 0 is the root of 1. We then set the parent of 5 to be 0. And what this does is that it sets 5, which used to be a root, now as a child of 0. And all of the elements that used to be in the tree rooted at 5 now have a root of 0. And now these two trees have been unioned. Now we have the basic idea. Let's discuss how we can implement this in code. We initialize this array called parent, where parent of I gives a parent of the object I. Initially, each element is their own individual group, so we initialize the array with parent of I equals I. Next, we implement this function find of x, which finds the root of the tree that contains x. So first, if the parent of x is not itself, then we know that we have not yet reached the root of the tree. So we travel upwards the tree by one step by calling the find function recursively on the parent of x. Otherwise, we know that we have reached the root of the tree, so therefore we just return x. And finally, we define the union function, which joins the trees containing x and y. So as we've seen before, we first need to find the root of y and the root of x, and we then set the parent of one to be the other. So that is the algorithm, and now let's discuss the complexity of this algorithm. If the data structure contains n elements, then on average the height of the trees will be on the order of log of n. Since both the find and union operations involve traversing up the trees at most 2 times, the time complexity of both functions is O of log of n. The space complexity will be O of n owing to the parent array, which will have length n. Alright, I hope this video gave you a better understanding of the union find data structure now.
I mean, this doesn't make sense unless the nodes are... I guess the nodes have to be sorted by order and they have to be represented with numbers. So it goes from... Then that I can see that makes sense. Because then you can... The nodes are gonna be... You're gonna find on the index here. But otherwise... It doesn't make a lot of sense.
Okay, so now we're going to talk about the union and find operations we can do on the union find, or the disjoint set. This is the video where I demystify how those actually work internally. So to create our union find, the first thing we're going to do is we're going to construct a bijection, or simply a mapping between our objects and the integers in the range 0 inclusive to n non-inclusive, assuming we have n elements. So this step in general is actually not necessary, but it's going to allow us to create an array-based union find, which is very efficient and also very easy to work with. So if we have some random objects and we want to assign a mapping to them, then we can do so arbitrarily, as long as each element maps to exactly one number. So that is my random bijection, and we want to store these mappings perhaps in hash tables, so we can do a lookup on them and determine what everything is mapping. Next, we're going to construct an array, and each index is going to have an associated object, and this is possible through our mapping. So for instance, in the last slide, A was mapped to 5, so slot 5, or index 5, is going to be A's slot. So what you see in this picture is at the top is that array we just created, which contains our mapping. And in the center is just a visual representation of what's going on. The value in the array for each position is currently the index which it is at. This is because originally every node is a root node, meaning it maps to itself. But as we perform the instructions on the left of unifying groups together, or objects together into groups, we're going to find that we're going to change the values in our array to map to other layers. And specifically, the way we're going to do it is for some index I in our array, index I's parent is going to be whatever index is at position I. So, for instance, if we want to unify C and K, we look at C and K, and we discover that C has a root node of 4 and K has a root node of 9. So either C is going to become K's parent, or K is going to become C's parent. And that shows that K's parent is going to be C. So now
I guess here... I guess it's because I didn't see the union here. Yeah, because it's changing the parents. That makes a lot of sense. Because I was trying to understand this first, and then I didn't realize this part here. So in the first iteration, it doesn't matter because it's gonna be different because everyone is on the same set. But then it applies the union, and then that's where it creates the link from the parents to the nodes to get the connection between the edges. I think I understand now how it works. And I wanna check to see if this works here, because I'm not 100% sure. Well, I think it's sorting by the values there. That's why it's index true, I think. Yeah, not the values, the weights. No, it has to be the edges. Yeah, but it has to be the weights actually of the edges, I think. Not really sure, actually. A list of edges in the form UV W. Yeah, so it has to be the weight, I think. It's sorting by the weight from smallest to highest. And it then returns the list of this from smallest to highest weight. I think that's the case, yeah. And then it loops through this from the smallest to the highest in order to create the union thing. Yeah, I think this is correct. I'm pretty confident now.
index 9, which is K position number 4, because I know that C is 4. So next, f and e, we're going to do a similar type of thing, and I'm going to say that f is going to s parent is going to be e. So at s position, which is 1, remember is 0 because e is 0. Same thing for a and j. But here's where things get a bit more interesting. So now I want to unify a and b. So if I look, a has a 6 in itself, but 6 is j. So I know that a is root node for group means j, and b is a single node because it's a subloop. And then I'm going to merge smaller components into larger ones. So now b is going to point to j because the green group's root node is j. So now I want to merge c and d. So I find the root node of d, which is d, and find the root node of c, which is c. And I'm going to merge the small component d into the larger component, which is the orange group. So now d is going to be orange group. Now I want to merge d and I, so same thing happens, and I now points to c. Now I want to merge l and f. So s parent is e, so I'm going to merge l and b into the red group. I want to merge c and a. So this is an interesting example. So I find the c's root node, which happens to be c. I find a's root node, which is j. So now the component orange has 4 elements, the component green only has 3. So I'm going to merge the green component into the orange component. So now j is going to point to c. So I want to unify a and b. So if I go up and follow the parent nodes until I reach a root node, a parent is j, j parent is c. So I know that a belongs to the orange group. If I do something with b, I also discover that these parents also c, which is the orange group. So I don't need to unify them, they're already unified together. So h and j, g, they currently belong to groups, so I'm going to try to merge them into a new group, so I'm going to do blue group. So h and f. So if I look, h is parent is g, and f parent is e. The right component is lighter, so I'm going to merge the blue group into it. And now since g was the root node, I need to point to e, which is also the root node. Now I want to merge h and b. So h's root node is e, if we follow the chain from h to g to e, and b's root node is c, because we go from b to j to c. So now since the orange component is lighter than the red component, I'm going to point the root of the red component to the root of the orange component, so e now points to c. Okay, I know that in this example, I'm not using a technique called path. They currently don't have groups, so I'm going to try to merge them into a new group, so I'm going to do blue group. So h and f. So if I look, h is parent is g, and f parent is e. The right component is lighter, so I'm going to merge the blue group into it. And now since g was the root node, I make a point to e, which is also the root node. Now I want to merge h and b. So h's root node is e, if we follow up the chain from h to g to e, and b's root node is c, because we go from
Yeah, but here it doesn't say anything about the one that is larger. And I think it doesn't matter. Yeah, I think it doesn't matter.
from b to j to c. So now, since the orange component is larger than the red component, I'm going to point the root of the red component to the root of the orange component, so e now points to c. Okay, and note that in this example, I'm not using a technique called path compression. This is something we're going to look at in the next video, which is an optimization on the union find. To summarize, if we want to find out which component a particular element maps to, what we have to do is find the root of that component by following all the parent nodes until we reach a self-loop or a node whose parent is itself, and that will uniquely determine which component that element belongs to. And to unify two components together, what we do is we find the root nodes of each component, and then if the root nodes are different, because if they're the same, then they belong to the same component already, so if they're different, make one of the root nodes point to the, become the parent of the other root node. So just some remarks about this unified data structure. So in general, we don't really ununion elements, just because this would be inefficient as we have to update all the children which point to that node, we don't have access to those, but we could probably in theory keep track of that. I just don't see any application currently, but there might be. Also remark that the number of components in our union find is not equal to the number of root nodes remaining, because each root node is responsible for a component. And also remark that the number of root nodes never increases, it always decreases, because all we do is unify components, so components only get bigger and bigger and bigger. So now I want to talk about the complexity of the union find. So I said in the first video that the union find has an amortized time complexity. However, the implementation I just showed you does not have an amortized time complexity. Not yet, not without the path compression, which is something we're going to look at in the next video, which is what makes the union find an absolute beast of a data structure. You must watch the next video. But just as an example, if we need to check if h and b belong to the same group or a different group, it's going to take 5 hops in the worst case, and well, potentially much more. So h, we find the root node, which is c, and then we go from b, and then find the root node, which is also c. So this takes quite a few hops. So the next video I'm going to be covering path compression. So absolutely make sure you watch that video. It's what makes the union find so great. And also, if you're interested in some source code for the union find, go check out my GitHub repository of all these data structures I've been covering. So guys, thanks for watching, and I'll catch you next time.
Python implementation. It's important to note that the above implementation uses an adjacency list representation of the graph, but the algorithm can also be implemented using an adjacency matrix representation. Applications of Kruskal's algorithm. Kruskal's algorithm has a wide range of applications.
And now let me because I changed the algorithm there.
Kruskal's algorithm. Kruskal's algorithm can be implemented using various data structures. The disjoint set data structure is used to here. Graph is a dictionary containing the following fields. Vertices, the number of vertices in the graph. Edges, a list of edges in the form u, v, w, where u and v are the vertices connected by the edge and w is the weight of the edge. The find and union functions are used to implement a union find data structure, which is used to keep track of which vertices are connected to each other in the minimum spanning tree. It's important to note that the above implementation uses an adjacency list representation of the graph, but the algorithm
I think I'm gonna remove this thing here because I changed the algorithm.
Kruskal's algorithm is a powerful and versatile algorithm for finding the minimum spanning tree of a graph. It is used to find the optimal solution for a wide range of problems, including network design, image segmentation.
I'm thinking about it, whether or not I should put more stuff here to explain how it works. I think I'm gonna do that. Oh yeah, there's the comments here. I think this is good enough, probably. I think it's done like this. Yeah, I think it's with A. But maybe not. Maybe it's with E. Yeah, I think it's with E actually. And then the union function is applied to merge the sets if the parents of the nodes are different. You find in union function combine, make sure there are no cycles. Just to make sure. Maybe it doesn't. No overlapping subsets. I don't know how to write this because it doesn't matter that much. Yeah, it has no cycles, okay. I thought that was the case, but I wasn't sure. Because it doesn't make sense there if it's checking to see. I think it checks to see if the parents are different here to prevent the cycle. And that's how it decides whether it's gonna make the union or not. And the weight of the edges in the first line, the parents is a list that is used to map the nodes to their respective sets. It starts with each having its own set, but then the union function is applied to merge the sets if the parents of the nodes are different. Define the union function, combine, make sure. So, but then the union function is applied to merge the sets if the parent of the nodes are different. Merge the sets, the parents are the nodes are different. Yeah, I think that's correct. Define the union function, combine, make sure there are no cycles, returning the end, the minimum. Okay, I think that's fine. So I'm gonna move on to the next one. I think off stream I'm gonna continue to do the articles, and then tomorrow I'll probably come back and do the same thing that I'm doing here, reviewing them. And if I don't see anything wrong, then I don't change anything. And then if I think the way that I'm doing now is probably the best, because if I have some questions, that's probably the questions that other people are gonna have that don't know about the topic. So by clarifying them, it makes the article better, I think. Because I can make the article from a beginner's point of view. It's gonna help more people, I think. A Bellman Fords. Yeah, this one I studied because of arbitrage, but I don't really know that well, so. But I think it's not gonna be that difficult to understand. It's you should find cycles on a graph that has negative weights. And that's the main difference between Bellman-Ford and Jaskrat, or however you say this shit here.
Introduction to Bellman-Ford's algorithm. Bellman-Ford's algorithm is a powerful tool for solving single-source shortest path problems in a graph. It is particularly useful for graphs that may contain negative edge weights. In this article, we will explore the Bellman-Ford algorithm in detail, including its time and space complexity, its applications, and its limitations. What is Bellman-Ford's algorithm? Bellman-Ford's algorithm is an algorithm for finding the shortest path between a given source vertex and all other vertices in a weighted graph. It is a dynamic programming algorithm that uses a relaxation process to gradually improve the estimates of the shortest path from the source vertex to each other vertex in the graph. The algorithm starts by initializing the distance from the source vertex to itself as 0, and the distance to all other vertices as infinity. It then repeatedly relaxes each.
Yeah, so it's very, very similar to the way that the other one works, with the flag variable to keep track and then guess the smallest by looking through the neighbors and then updating the edges, which people call this relaxation. I don't understand where the term comes from. It seems weird to me, but yeah. First time I heard it, I have no idea what does it mean to relax an edge.
It then repeatedly relaxes each edge in the graph, updating the distance estimates as necessary. The algorithm stops when it has completed v1 iterations, where v is the number of vertices in the graph. Time and space complexity. The time complexity of Bellman-Ford's algorithm is O, v, where v is the number of vertices in the graph and e is the number of edges. This is because, in the worst case, the algorithm may have to relax each edge in the graph v1 times. The space complexity of the algorithm is O, v, as it only needs to store the distance estimates for each vertex. Applications of Bellman-Ford's algorithm. Bellman-Ford's algorithm has a wide range of applications, including shortest path problems. The algorithm can be used to find the shortest path between a given source vertex and all other vertices in a weighted graph, even if the graph contains negative edge weights. Detecting negative cycles. The algorithm can be used to detect the presence of negative cycles in a graph. If the algorithm completes a VTH iteration without relaxing any edges, then there is a negative cycle in the graph. Route optimization. The algorithm can be used to optimize routing in networks, such as telecommunications networks or transportation networks. Limitations of Bellman-Ford's algorithm. While Bellman-Ford's algorithm is a powerful tool for solving shortest path problems, it does have some limitations. These include poor performance on dense graphs. The algorithm has a time complexity of O, v, which makes it less efficient on dense graphs. Not suitable for graphs with parallel edges. The algorithm cannot handle graphs with parallel edges, as it treats each edge as distinct. Python implementation.
Okay, so it's creating all the nodes with infinite value, then they start at 0, then looping through the graph, getting the weights and nodes for the edge. Then if the distance of one node plus the weights is, if the distance of the node is greater than the weight plus the other, it updates the value. So it's very similar to the other one, the DGSCRAT. So I don't know how to say that. I always struggle to say that thing, the name of the guy. And then it checks for negative weight cycles. But I'm not 100% sure if this is correct though. So I'm gonna look into it. And this is gonna be the last one because it's almost, the time is up. Blah blah blah. But isn't it supposed to handle negative weights? I think the implementation is correct, but I don't understand why. Because in my mind, it was supposed to work with negative weights, so to calculate the cycle, the route. Yeah, but maybe this is wrong here. It doesn't make a lot of sense. Because it is the same as this one. No, but after it's updating. Yeah, this comes after it updates there, so that's the difference. Yeah, I think it is correct, the algorithm there. I'm gonna stop here. I'm gonna watch some more videos about this one off stream, just to be 100% sure. But I think there's a high probability that it is correct there. I don't see any reason why it wouldn't be correct that way. I just think it's strange because the way that I was thinking about it before is that it is supposed to handle negative weight cycles. And I did study this for arbitrage, but I did superficially because I was thinking about implementing other methods that would be more relevant to the blockchain situation. Yeah, so I'm gonna stop here. What I'm probably gonna do is study this off stream and then continue to do the articles. I think I'm gonna try to do either 3 or 4 today with ChatGPT, and then tomorrow I continue to review them where I stopped.
Hey everyone.
Yeah, so if I don't come back tomorrow, then most likely 2 days from now I'll come back.